We talked about the limits to solubility last time, where we said saturated, unsaturated, and supersaturated. Okay, so what are the kinds of things that limit how soluble something is? Why can sugar be so very soluble, but other things maybe I can only dissolve a little bit? So it's affected by three things: size, polarity, and charge. Now, when we say something is dissolved, what we mean is that each individual particle, each individual molecule is surrounded by water. So this maybe is a sodium ion. It's not touching the chloride, right? They're completely separated and there's water in between them. Ooh. So in order to dissolve something, it has to be completely separated. And that's why the solution is clear. You can see through it, okay? But in order to do that, the water has to be attracted to those particles. So if I have sodium chloride, I've got a positive charge and a negative charge. And so the water is going to be attracted to that because water is polar. Remember, we talked about polar and nonpolar. So water has that one side, the oxygen side that's negative. That's going to be attracted to the positive of the sodium. So if you look at the picture here, there's the positive. This is the oxygen pointing there. This is the oxygen pointing there. The hydrogens are sticking out at us, so the oxygen's pointing there. So the water molecules turn and rotate so that the oxygens face the positive particle and the hydrogens are facing the negative particle. All right, size is also going to affect it. So we have some things that otherwise should be soluble, but they're just so dang big we can't dissolve them. For example, cotton, you have clothing made out of cotton. That cotton is made out of a polymer, a really long molecule. And even though that molecule has lots of ways that it's going to attract the water, it's just so big, it's really impossible for water to completely envelop it and separate it from everything else. And then I mentioned polarity as well. So if we have anything that's polar, well, we said sugar is polar, right? So sugar dissolves really easy in water because it is also polar. Okay, so those three things are going to affect whether or not we can dissolve stuff. All right, saturation. So we got similar pictures here of dissolving things where we get darker and darker as we dissolve more stuff. But these two are about the same color. Now, you can't see from where you are because the dots are almost the same color as the background. But in both cases, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 red dots floating up here. But in this one, I have several on the bottom. So 9 is kind of the limit. We'd say this is saturated. And if I try to add any more, it's not going to dissolve. Okay, so saturation is the limit at a given temperature. So when we have saturation, we can talk about the solubility, and that is how much you can dissolve when it is saturated. So you can see that for sugar, the solubility at room temperature is 210 grams per 100 grams of water. So you can get twice as many grams of sugar as you can of water, and it still dissolves. Now, how does that work? Well, remember that water is a lot smaller than sugar. So it was 342 for the sugar was the mass, and water was 18. So even if we have the masses so different, where the mass of the sugar is greater than the water, we still have a lot more water molecules. I think it's around 15 water molecules at that point that surround the sugar. Salt, on the other hand, has a limit of 36. Okay, so we can't quite get a mole of salt to dissolve in 100 grams of sugar. So different things are going to have different solubilities. And remember, we talked about in the last chapter that it's going to be for water, polar things are going to be more soluble. But if I did this for oil, the limit would be very, very low. Now, it might dissolve like 0.001 grams or something like that, but basically it's going to be insoluble. All right, supersaturation happens when we go beyond that limit. And usually what happens is we've dissolved it at a temperature, usually a higher temperature where that will work, and then let it cool back down. And because it's already kind of stable being dissolved, the molecules are already separated, then they don't start to precipitate out right away. So that word metastable, remember that means that it's kind of okay the way it is, but if you disturb it too much, then you're going to change the situation. So it's like sleeping on a little outcropping on the side of a mountain. If you roll over in your sleep, you're going to fall down the mountain. You're fine as long as you're holding still. Well, with solutions, if they're super saturated, if you add a couple of crystals or if you shake them, that's how you can get it to precipitate out. Okay, so what we're going to do is I'm going to have you take a look at your crystals and, I got to go grab the balance. I want you to weigh the container and then we're going to record what the mass of your container is, because as we were heating, you probably lost some of the water, right? Not all of it stayed in that container. So while we all started with 50 milliliters of water, you might have ended up with less, okay? And we're going to see if we can figure out what the concentrations of these different things are. So I'm going to, let's see, end this. I thought I had some questions in there, but apparently I did not. Well, we'll skip that part, but let's take a look at what we have here with our mixtures. So I did 75 grams. And this right now has just a few crystals right at the top. It's mostly still a clear solution. Even on Tuesday, this really didn't have anything with it. So it took a lot of evaporation for this to get down. Now, the two that were 50 didn't have any crystals last week, but I think when you guys were looking on Tuesday, they did, and they're starting to have crystals now. So with the drier weather, there's more evaporation. So we got quite a few crystals now. So it's kind of hard to tell the difference today between what the crystals were doing. But do you remember on Tuesday, did these that had the less water or the less sugar, did they look different than the others? You don't remember? What do you think? Clayton? Didn't have as many crystals? I would agree. They had fewer crystals. All right. Let's see. Here's the 151 and the 125. These barely have any liquid in them at all now. Okay. So they're like almost entirely crystals. There's a tiny bit of liquid in this one, almost none in this one. So we can conclude that we're going to grow crystals faster if we have higher concentrations. That's one thing that we might look at. Now, the other thing that we might look at is the size of the crystals, and that's why I put sticks in here. So on here, I have a cluster of crystals, but I can actually see through some of the crystals. I'm going to hold this really close to the camera, and you might be able to see that, especially this one on this side here, you can kind of see through it. So there's a crystal that I would guess is probably 0.5 centimeter that is clear. The clear ones are what we call single crystals. And when you get rock candy, you have lots of those large single crystals. That's kind of what you want in your candy. But when you have like sugar that you would, spoon out of a jar, they're teeny tiny crystals, and that wouldn't be very interesting to eat. They're not going to have that crunch in them. Let me see if I can get one out of here. This one has one of those. Okay. So the solutions that were less concentrated were able to get more of these larger crystals, okay? So while the more concentrated ones grew faster crystals, the less concentrated ones grew larger crystals. Okay, so now we're going to switch gears back to this guy, and I will save the other sheet to collect on Tuesday when more people are here. And that way, everybody can have that information to turn in. So save those, don't lose them. If you have them, bring them back. So most desserts rely on crystallization of sugar to a certain extent. So this is a picture of rock candy. The crystals can give a grainy texture, can give it a crunchy texture. And you might ask yourself, well, is that what I want in my food? And sometimes it is. So for rock candy, it just really wouldn't be rock candy if it didn't have that crunch to it. And you can see on this piece here, the left bottom one, there's a little clear spot there, so you can really tell that's a single crystal. And on the top one, there's kind of a single crystal sticking up about midway from midway, a little bit towards the left. All right. So we want large crystals when we have rock candy. Sea salt, if you ever had food that has sea salt in it, the whole purpose of it is to have large crystals. Because once you put it in liquid, it's dissolved. It doesn't matter whether you started with sea salt or regular salt, it's all salt. But if you sprinkle it on the top of something, it's given a little bit of crunch to it. So you want that. If you want something that has like a snow cone or something like that, you might want a little bit of crunch in there. Some people like to chew ice, but not chew it so much as crunch the ice. So you might like that. But a lot of times there are sharp edges, and those sharp edges can interfere with some of the other food things that are in there. Not on a molecular level so much as on the clusters of molecules. Now, if you want something that is, oops, yours is not advancing. Come on. There we go. Okay. Small things. Pralines, these tend to look cloudy. You might think of like maple sugar candy. They have kind of a little bit of a grainy texture to them. They're softer. If you go to caramels, you really don't want that grainy feel at all. With ice cream, you want it to be smooth, right? So you usually want those crystals so small that your tongue doesn't really get that grainy texture, except maybe on the praline. Okay. So by controlling how quickly or how quickly we're forming or how concentrated our solution is, we can control what that grain size is. Okay, so sometimes people like to make ice cream at home. Knowing how to make those crystals really small is really key to making smooth ice cream if you're going to make that at home. All right. So thinking about how crystals form, once you have a solution, if it is saturated or supersaturated, the molecules are going to start to get together. They're going to start to cluster if there's enough of them nearby because they're attracted to each other. And we call that a nucleation site. So the nucleus is like the middle of something. This is the start of a crystal. It's going to be the middle of the crystal. Okay. So if I have just one of these, then it has a lot of room to grow. But if I have lots and lots of nucleation sites that are close together, it's not going to be too long before they bump into each other. So if you had to share a bedroom with siblings when you were little, as you get older, you're kind of getting into each other's space. So if you have 2 or 3 kids in the same bedroom, you're bumping into each other right away. Okay. But if you have your separate bedrooms, maybe you get along a little bit better. So fortunately, we were able to have my 2 daughters in separate bedrooms because they were at each other's throats all the time. It would have been nuclear war in our house if they didn't have separate bedrooms. All right. So many nucleation sites mean that they're going to be small crystals because they're going to run into each other before they have a chance to grow. All right, so solubility of sugar and salt. We said sugar dissolves really well and salt dissolves, but not quite as well. And you can see, I mentioned this the last time, last week, that salt doesn't change a lot with temperature, a little bit. It gets a little bit higher, but not a lot. But sugar, the more we heat it up, really we can dissolve a lot more. So we said at room temperature, 200 grams per 100 milliliter. By the time we get to the boiling point, here's 100 degrees, it's almost 500 grams that you can dissolve at the boiling point. Okay, so that is a lot of sugar that can get dissolved. We can use this to help us decide or help us determine how big those crystals are going to be. So if I take it to the boiling point and dissolve 450 grams, and you guys did half the amount of water, so let's think about half the amount that you did, 75 grams, let's see, this is per 100. Yeah, 150 would have been like 300. There we go. Okay. So we probably could have gotten that dissolved right around 75 degrees. Okay. As we cool it down, as the temperature goes to the left, that's no longer soluble and you start forming crystals. So when we had lots of sugar dissolved, it wanted to form those crystals right away. Whereas when we started closer to the solubility at room temperature, when we had 100 grams dissolved, as it cooled down, it got to almost room temperature before it needed to start those crystals. And when we had 50 grams, it had to evaporate some off before it could form some crystals. Okay, so it takes more and more time for the crystals to start to form. The longer it takes for the crystals to form, the fewer nucleation sites there are. Okay, so what determines the nucleation? Fast nucleation is going to give us small particles. Slow nucleation is going to give us large particles. Okay, so fast happens when I start with something concentrated. Slow is when it's more dilute. But if it's too dilute, I might not get any crystals at all. Okay. We can also get those crystals to form by doing some things. Major thing being stirring. Yes. Okay, so fast nucleation, rapid motion. So stirring really, really quickly. We had some of our students in lab making some maple sugar pralines, and what they had to do is as soon as they pulled the syrup off of the stove, they had to stir it really, really quickly to try and get those crystals to start forming so they would be small crystals. So vibrations and stirring make lots of little tiny crystals. Or if you have rapid changes in solubility. So if you have high concentration or if you're cooling it really quickly, like if you stick it in the refrigerator, it's going to start cooling down really quickly. For our slow nucleation, we kind of want to do the opposite. So to change the concentration slowly, we might want to have evaporation. Okay, so water evaporated off of all of our rock candy, but I hadn't started forming any crystals in the 50 grams of sugar or the 75 grams of sugar until it started to evaporate. So it took cooling down to room temperature and then evaporating, which is slower, to get that to happen. And so we got larger crystals there. So gradual cooling, evaporation, and then we can also end up with what we call supersaturation. That didn't happen in any of these cases where we didn't get any crystals to form, but you could get no crystals to form that way. All right, so little crystals, smooth ice cream, I want to keep stirring it. This is why you have to stir ice cream as you're making it. What happens if you don't? Well, big crystals of ice are sharp and they're going to puncture the fat molecules, the little blobs of fat that make up the ice cream. Well, instead of that having a nice smooth texture on your tongue, it's going to be pasty. So you don't want that pasty feel on your tongue. You would rather have a nice smooth feel on your tongue. And so it's important not to have those large crystals. You want it to cool with lots of stirring, but it also helps if you cool it really, really quickly. Has anybody ever had ice cream made by liquid nitrogen? So liquid nitrogen is very, very cold. And that's going to cool it down super fast, which means you're going to get lots and lots of crystals. And so it helps to make it smoother by cooling it down really rapidly.
Yeah.
Yes.
As you said, like those small bowls.
Yes. So the Dippin' Dots, you probably had Dippin' Dots before, right? Teeny tiny, those are made by liquid nitrogen as well. And as they melt, they should be smoother than regular ice cream because they are cooled so quickly, you get lots of teeny tiny crystals in there. Okay. So, other things that we might be trying to crystallize might be like chocolate. So chocolate forms crystals as it cools down, but its melting point is a lot closer to room temperature. So next week, we'll talk a little bit about tempering chocolate. There are 6 different kinds of crystals that you can get with chocolate. And they all have different melting points. And if you get the ones that have the lowest melting points, then your chocolate is all crumbly and it's more pale in color and it doesn't have that nice smooth flavor to it. So if you've ever had chocolate that maybe it's like sat in the car and it's heated up and cooled down and heated up and cooled down, and you open it and it just kind of falls apart, that's crystals forming at a lower temperature, and those crystals aren't pleasant for us. But if you get chocolate that, like when you bend it, it snaps, so you get a nice snap to it, and it's smooth and dark and shiny. That's what we call tempered chocolate. And so that has what we call crystals number 5. Okay, so we'll talk about tempering next week for the crystals of chocolate, but the same rules apply. If we want to have those nice crystals for tempered chocolate, we have to get those crystals to grow slowly. We don't want to take the chocolate and shove it in the refrigerator because that's going to cool it too rapidly and get teeny tiny crystals. Okay. All right. That's all I have. So since our experiment didn't really work out the way I wanted it today, I guess we're done for today. But do bring back your guided notes and bring back your rock candy crystal growth sheet next Tuesday. Have a good weekend.